Deep underground, behind dozens of meters of solid rock, Iranian scientists believed they'd found the perfect shield. The logic seems sound. No air force in the world could reach them down there. But here's what they got wrong. The deeper you bury a nuclear program, the more precisely the US military has learned to target it. What we're going to show you is the weapon system built specifically to solve that problem, and why no bunker Iran can realistically build or operate will keep its program safe. The bunker strategy: why Iran went underground. Iran didn't decide to go underground on a whim. It watched what happened to Saddam Hussein's nuclear ambitions after the Israeli strike on Osirak in 1981. And it watched what happened to Libya's Gaddafi after he gave up his weapons program and was removed anyway. The lesson Iran took from both of those situations was simple. If you want a nuclear program to survive, you can't leave it sitting on the surface where anyone with a GPS coordinate and a large enough bomb can reach it. So Iran started digging. The most well-known result of that strategy is Fordow. It sits near the city of Qom, carved into the rock of a mountain rather than simply buried beneath flat ground. The Iranians chose that site deliberately. The mountain itself adds protection that poured concrete alone can't replicate. At reported depths of around 80 to 90 meters below the surface, the facility was designed from the start with one specific threat in mind: American and Israeli air power. The thinking behind it is straightforward physics. The deeper a structure sits, the more material a warhead has to pass through before it reaches anything worth destroying. At 80 meters of rock and reinforced concrete, you're outside the reach of almost every conventional airdrop weapon ever built. Iran's engineers knew the specifications of the munitions that existed when Fordow was being constructed, and they built accordingly. But depth wasn't the only layer of the strategy. Iran deliberately spread its nuclear work across multiple sites: Natanz for centrifuge operations, Arak for a heavy water reactor, Isfahan for uranium conversion, and Fordow for the enrichment work considered most sensitive. The logic of dispersal is that any adversary planning a strike has to hit all of them simultaneously, or accept that whatever they don't hit will survive and continue operating. Miss one, and the program lives. There's also the political dimension to dispersal. Striking a single facility can be framed as a limited, targeted operation. Striking 6 or 8 sites scattered across a country the size of Iran starts to look like a war, and that calculus has historically made Western governments hesitant to act. For years, that combination, depth plus dispersal plus political complexity, gave Iran genuine protection. Defense analysts in Washington and Tel Aviv debated openly whether Fordow was simply out of reach. Some concluded it was. The Iranians were following that debate closely, and what they heard gave them confidence the strategy was working. What they didn't fully account for was that the US military was following the same debate, drawing the opposite conclusion, and quietly funding the answer. That answer didn't come from diplomacy. It came from a weapons program that had been running in the background for years, built around a single question. What does it take to reach a target that conventional munitions simply cannot touch? The weapons built to answer the bunker, the GBU-57 Massive Ordnance Penetrator, doesn't have a subtle name, and it wasn't designed for subtle work. It weighs 30,000 pounds. To put that in context, that's roughly the weight of 2 full-grown African elephants, packed into a single weapon and dropped from altitude at high speed. The US Air Force developed it for one purpose: reaching targets that nothing else in the arsenal could touch. The way it does that comes down to engineering that looks almost crude until you understand the physics. The outer casing is hardened steel, thick enough to survive the violent deceleration of punching through rock and reinforced concrete without the weapon breaking apart before it reaches its target depth. Inside, a delayed fuse gives the warhead time to travel down through the layers of material before it fires. The result is a weapon that can penetrate more than 60 meters of reinforced concrete and considerably more in softer ground before the 5,300-pound explosive fill detonates in whatever space it's reached. That number matters. 60 meters of reinforced concrete is a different problem than 60 meters of mountain rock, and the distinction is worth holding on to because it becomes important when we get to Fordow specifically. The only aircraft in the US inventory capable of carrying the MOP is the B-2 Spirit, and it carries 2 of them. That's not a limitation of the aircraft so much as a reflection of how big the weapon actually is. The B-2's bomb bay was modified specifically to accommodate the MOP, meaning the Air Force committed real money and engineering time to making this delivery possible. You don't do that for a contingency plan. You do that because someone made a decision that this capability needed to exist and be ready. The MOP didn't appear from nowhere. It was preceded by the GBU-28, which became famous during the Gulf War in 1991. A 5,000-pound weapon that could punch through about 6 meters of concrete. At the time, that was enough to threaten the bunkers Saddam Hussein was using. But as Iran and North Korea watched that conflict and started building their own underground infrastructure, they built deeper. The GBU-28 stopped being a credible threat to the facilities they were constructing. The gap between what the U.S. could deliver and what adversaries were burying kept widening through the 1990s and into the 2000s. The MOP program was the direct institutional response to that gap. Congressional documents from the mid-2000s name Iran and North Korea explicitly as the threat scenarios driving the weapons development. The U.S. government wasn't being subtle about what this was for. The MOP reached operational status around 2011, and the Air Force has continued refining it since. At least 2 upgrade programs have improved its guidance systems and fusing to address specific feedback about penetration, performance against particular soil and rock compositions. That last detail is worth sitting with. The upgrades weren't generic improvements. They were responses to specific target characteristics, which means U.S. planners have been modeling Fordow and facilities like it in enough detail to identify exactly what adjustments the weapon needed to defeat them. The MOP wasn't just built to reach underground facilities in general. It was progressively refined to reach the specific ones that matter most. Penetration depth alone, though, is only part of the equation. Getting a 30,000-pound bomb to the right coordinate over defended territory without being shot down before it releases, that's a separate problem entirely, and it required a separate solution. Delivery, precision, and the platforms that make it work. The B-2 Spirit is the reason any of this works. Without a platform that can carry the MOP into defended airspace and release it accurately, the weapon is just an engineering achievement sitting in a hangar. Stealth is what converts that engineering into an actual military option. The B-2's radar cross-section is roughly the size of a large bird, a product of its flying wing shape, radar-absorbent surface materials, and the careful internal routing of engine exhaust to reduce heat signatures. Iranian air defenses are built around radar. They need to detect, track, and engage an incoming aircraft in a sequence that takes time. The B-2 breaks that sequence at the first step. If the radar can't produce a reliable track, the missiles that depend on that track can't fire effectively. The aircraft reaches its release point, drops its payload, and exits before the defense system has resolved what it was looking at. Precision is the other half of that equation. The MOP uses a combination of GPS guidance and an inertial navigation system that runs independently in case GPS signals are jammed or degraded. Together, they put the weapon within a few meters of its target coordinate. And that accuracy is what makes sequential strikes possible. You can drop the first weapon into a specific entry tunnel, then drop the second through the hole the first one created, driving the destruction progressively deeper into the structure. That's not a theoretical concept. It's a documented strike methodology the Air Force calls re-attack, and it was specifically developed to address cases where a single pass isn't sufficient to guarantee destruction. But before any weapon leaves the aircraft, intelligence has to do its work. ISR, intelligence, surveillance, and reconnaissance, is what tells planners where exactly to aim. Satellites, signals collection, and aerial reconnaissance over years of observation have produced detailed models of facilities like Fordo, where the access tunnels enter the mountain, where the ventilation shafts run, where the power infrastructure connects, and where the internal chambers sit relative to the surface above them. Dropping a weapon accurately onto a coordinate is simple. Knowing which coordinate to give it, the one that collapses the right tunnel or severs the right shaft, is the product of years of collection work. The weapon and the intelligence system feeding it are inseparable. Now factor in the B-21 Raider, which has entered operational service and carries the same heavy payload capability as the B-2. The B-21 was designed with lessons from decades of stealth operations folded into its architecture from the start, rather than retrofitted over time. Its manufacturing approach also means the Air Force can build more of them at lower cost, which changes the calculus around how many aircraft are available for a given mission. The B-2 fleet is small, 20 aircraft total, and not all of them are mission-ready at any given time. The B-21 is intended to grow that number considerably. More aircraft means more simultaneous strike packages, which matters directly for the dispersal problem Iran built its program around. The more sites you can hit at once, the less the dispersal strategy protects. Iran's engineers designed Fordow with the threat environment of the early 2000s in mind. The delivery systems flying today are a generation past what those engineers were modeling, and the generation coming next is further still. The physics problem Iran can't solve. Here's the constraint that no amount of concrete or political maneuvering can fix. The deeper you bury a facility, the harder it becomes to actually run one. Enrichment centrifuges are precision instruments. They spin at tens of thousands of rotations per minute and require stable power, stable temperature, and constant maintenance. The deeper underground you place them, the more complex and expensive the infrastructure keeping them alive becomes. Ventilation shafts to remove heat, power lines running down from the surface, supply tunnels wide enough to move equipment in and out. Every one of those systems is a structural dependency. Sever the ventilation and the facility overheats. Cut the power and the centrifuges stop. Collapse the access tunnel and no one gets in or out. The mountain protects the facility from above, but it also creates a set of choke points that a sequenced strike package is specifically designed to exploit. That's the part of bunker busting that rarely gets discussed. It isn't just about driving a warhead through the roof. A coordinated strike targets the tunnel entrances, the ventilation outlets, and the external power nodes in a sequence that leaves the interior intact but completely inoperable. A facility that survives a strike in that condition is still offline for months, possibly years, while the damage is assessed and the infrastructure rebuilt. From a military planning perspective, that outcome is nearly as good as destruction, because the time it buys is the point. Now apply that to Fordow specifically. The facility sits at a depth where the MOP's penetration capability against the rock composition of that mountain sits at the edge of what's publicly confirmed. And US officials have acknowledged that tension openly, then pointed to the upgrade programs that followed. What those upgrades addressed, based on what's been reported, was exactly that margin. The weapon was improved to close it. Iran's engineers face a dilemma with no clean exit. Push the facility deeper to stay ahead of penetration capability, and you make the operational problems worse. Longer ventilation shafts, longer supply lines, more surface infrastructure that satellites can image and strike packages can target. Stay at current depth and accept that the MOP, delivered accurately and sequentially, puts the facility at genuine risk. There's no depth that solves both problems at once, because the geological constraints that limit what a bomb can reach are the same constraints that limit what an engineering team can build and sustain. The bunker was always a bet that the weapons pointed at it would never quite catch up. That bet is no longer paying out. Where this leaves Iran, no underground facility survives indefinitely against an adversary with the will to use what it has built. That's not a political statement. It's the operational conclusion that falls out of the physics and the engineering on both sides. Iran's nuclear timeline has always been shaped by diplomacy, sanctions, and internal politics. What's changed is that the military dimension now adds a hard constraint that those other factors can't negotiate around. The US has the weapon, the platform, the intelligence picture, and a demonstrated willingness to act when it judges the moment right. Israel has struck Iranian assets before and has been explicit about what it will not accept. Both of those realities exist independent of whatever is happening at the negotiating table. The bunker gave Iran's program survivability it didn't have before. What it didn't give Iran was a permanent solution. It gave the program more time. And time, in this context, is running out faster than the mountain overhead would suggest. The bunker was Iran's answer to air power, and the MOP was America's answer to the bunker. That exchange is effectively over, and only one side came out ahead. The upgraded F-22 Raptor is challenging global defense norms. With enhanced stealth, improved engines, and advanced sensor fusion, its air superiority is redefined. Critics warn these changes could trigger an arms race, while others argue it secures U.S. dominance. Meanwhile, China and Russia are investing in next-generation fighter technologies to lead the innovation race. As Beijing and Moscow ramp up their modernization efforts, the critical question remains: can the F-22 maintain its supremacy, or will emerging platforms like the F-47 usher in a new era of aerial warfare? Join us as we uncover the cutting-edge upgrades of the F-22 Raptor, advancements so powerful they've captured China's attention. The F-22 Raptor is one of the most advanced fighter jets ever built, but it didn't start out that way. It began as part of the U.S. Air Force's Advanced Tactical Fighter program in 1981. The goal was to replace the F-15 and F-16, which were powerful but becoming vulnerable to new Soviet threats. The Soviets were developing advanced missiles, airborne warning systems, and new fighters like the Su-27 and MiG-29, which could challenge U.S. air superiority. To stay ahead, the U.S. needed a fighter that was faster, stealthier, and more advanced. Engineers designed the ATF to dominate in a future war, using cutting-edge technology like lightweight materials, better flight controls, and engines that allowed supercruise. Sustained supersonic flight without using fuel-hungry afterburners. Most importantly, it had stealth capabilities, making it nearly invisible to enemy radar. After years of competition, Lockheed YF-22 won against Northrop's YF-23 in 1991. While the YF-23 was stealthier and faster, the YF-22 was more maneuverable thanks to its thrust vectoring engines, which allowed it to perform sharp turns and outmaneuver enemies in close combat. Lockheed's design also had fewer risks, making it the Air Force's top choice. Over the years, the F-22 has received multiple upgrades to keep it at the top of the game. Originally built for air-to-air combat, it has been enhanced to handle air-to-ground missions with precision bombs, making it more versatile. Its avionics have been upgraded, including better radar and sensor fusion, allowing pilots to detect and track threats even more effectively. One of the biggest improvements is its stealth maintenance. When the F-22 first entered service, its stealth coatings required a lot of upkeep, but new materials have made it more durable and easier to maintain. This means less downtime and more time in the air, ready for action. The F-22's weapon systems have also been enhanced. It now uses improved AIM-9X Sidewinder missiles for short-range dogfights and AIM-120D AMRAAM missiles for long-range engagements. Additionally, new software upgrades have given it the ability to communicate better with other aircraft, improving its role in networked warfare. While the Air Force stopped producing the F-22 after building 186 jets, it has continued to receive technological upgrades. Some of these improvements come from lessons learned during the development of the upcoming next-generation air dominance fighter, and they have enhanced the fighter jet's ability to detect, track, and eliminate threats before they even know it's there. These technological upgrades have significantly strengthened one of the F-22's most critical advantages, its radar and sensor systems. The jet's AN/APG-77 radar allows pilots to spot enemy aircraft from extreme distances while staying undetected. This radar uses active electronically scanned array technology, which improves tracking and targeting while reducing the chance of being detected by enemy systems. Combined with powerful jamming capabilities, the F-22 can disrupt enemy communications and radar, making it even harder to counter. The F-22 doesn't just rely on stealth, it's also armed with some of the deadliest air-to-air weapons in the world. The AIM-120 AMRAAM missile is its primary long-range weapon, designed to engage enemy aircraft before they get close. For close-range combat, the AIM-9X Sidewinder offers unmatched agility, allowing the Raptor to take down threats even during high-speed dogfights. Additionally, the F-22 carries an M61 Vulcan 20mm cannon, a 6-barrel rotary gun capable of firing 6,000 rounds per minute. This provides a powerful backup for situations where missiles aren't an option. Speed and agility are key to the F-22's dominance. Its thrust vectoring nozzles give it unmatched control in the air, allowing it to perform maneuvers no other fighter can match. Whether it's executing high G turns, rapid climbs, or sudden dives, the Raptor can outmaneuver opponents with ease. This ability is critical in dogfights, where the slightest advantage can mean the difference between victory and defeat. Former pilots often describe flying the F-22 as effortless, with its advanced flight controls making complex maneuvers feel smooth and precise. This agility ensures the Raptor can engage and disengage at will, giving its pilots complete control over the battlefield. While the F-22 is already a technological marvel, ongoing software and hardware upgrades will keep it ahead of emerging threats. The F-3R, that is, Form, Fit, Function Refresh program, is enhancing the aircraft's avionics, increasing its processing power and sensor capabilities. These improvements will make the Raptor even deadlier, allowing it to integrate with next-generation systems and unmanned drones in future combat scenarios. The Air Force is also working on engine enhancements to boost efficiency and power, ensuring the Raptor remains capable of supersonic speeds without afterburners. These updates will extend the F-22's operational life, keeping it in service for years to come. Last year, Lockheed Martin successfully ran 6 flight tests to add new high-tech features to the stealth fighter. The U.S. Air Force relies heavily on its fleet of F-22s, and these upgrades will help keep the jet at the top of its game, possibly all the way into the 2040s. Some of the biggest improvements include a new infrared defensive system, advanced sensors, and special stealthy drop tanks that extend its range. At the 2025 Air and Space Forces Warfare Symposium, Lockheed Martin shared updates about these developments. Right now, the Air Force has about 180 F-22s, though 32 of them are older models used only for training and testing. Mike Shoemaker, a top executive at Lockheed Martin, emphasized the significance of the upgrades, stating that modern fighter jets must have enhanced vision, quicker threat detection, and extended strike capabilities. He mentioned that recent flight tests had concentrated on integrating advanced sensors to improve the F-22 Raptor's ability to track and engage targets from much greater distances, significantly boosting its combat advantage. While Lockheed Martin didn't share specific details about these sensors, the Air Force has been testing stealthy underwing pods on the F-22 for years. Many experts believe these pods house an advanced infrared search and track system, which would allow the Raptor to detect enemy aircraft without using radar, perfect for staying hidden while hunting down threats. Another major improvement coming to the F-22 is its next-generation infrared defensive system. Mike confirmed that Lockheed Martin is already under contract to integrate this technology, which will give the Raptor better missile warning capabilities and long-range detection. In simple terms, this means the jet will not only be better at spotting enemies, but also at avoiding surprise attacks. Lockheed Martin previously revealed that IRDS will use a distributed sensor system based on Hyperspeed technology, first introduced in 2022. Hyperspeed sensors provide a constant infrared view of the battlefield, helping pilots detect and track threats, even in complete darkness. So far, these sensors have only been fully integrated into F-5 advanced Tiger jets used by private military contractors. Now they're making their way to the world's most advanced stealth fighter. Mike's comments confirm that the F-22's new advanced sensor upgrade is different from the infrared search and track distributed system. This suggests that the Raptor may get even more advanced infrared tracking capabilities. Adding an extra infrared sensor pod alongside IRDS makes sense. Traditional IRST systems, whether built into jets or carried as external pods, typically use large, swiveling sensors to track targets from different angles. TAC IRST, the system being developed for the F-22, works differently. In 2017, Ken Merchant, a Lockheed Martin executive for the F-22 program, explained that there wasn't enough space inside the jet to install a full IRST system like the F-35's Electro-Optical Targeting System, or EOTS. EOTS mainly helps with air-to-ground targeting, but it also has infrared tracking capabilities. Even on its own, IRDS would be a huge improvement over the F-22's current ANAAR-56 missile launch detector, which only provides basic infrared warnings. TASI IRST sensors spread across the aircraft could help the Raptor detect threats more effectively, similar to how the F-35 distributed aperture system works. Using both built-in and podded IRST sensors together would be a game changer. As experts have explained, traditional IRST sensors can only detect a target's direction and movement, but struggled to determine its exact range. However, if two aircraft with IRST systems share data, they can quickly triangulate a target's position with precision. Lockheed Martin has already demonstrated this kind of teamwork using its Legion pod, which features an IRST-21 sensor. This system can provide high-quality targeting data and has been tested on various fighter jets. The F-22 was originally supposed to have an IRST system, but budget cuts removed it late in development. Now, with stealth technology becoming more common worldwide, the U.S. military sees infrared tracking as crucial. Unlike radar, which actively sends out signals that enemies can detect, IRST works passively. It simply listens for heat signatures, making it perfect for tracking stealth aircraft. IRST can also help radar systems lock onto targets more effectively, providing better accuracy without revealing the jet's position. One of the biggest advantages of IRST is that it's immune to electronic warfare. Modern enemy forces use jamming technology to disrupt radars, but infrared tracking can't be blocked in the same way. This makes IRST a powerful tool for detecting and tracking stealthy threats. Mike reassured that any new F-22 upgrades would maintain the aircraft's stealth capabilities. This is crucial as the U.S. faces increasing threats from advanced enemy aircraft and stealthy weapons. China, for example, recently unveiled two new stealth fighter designs, signaling rapid advancements in their air combat technology. He also emphasized the importance of detecting threats from greater distances in modern air combat. He explained that if an aircraft could sense and see farther, it would also be able to share that information with other units. The F-22 Raptor had already proven itself as one of the most advanced fighters, acting as a central coordinator for larger aerial teams. Mike noted that it could gather intelligence, guide other aircraft, and ensure air superiority. Lockheed Martin, alongside the U.S. Air Force and industry partners, had been working to enhance the Raptor's communication and networking abilities to further improve its role in battle. According to Lockheed Martin, the F-22 was the first combat aircraft to fully utilize an open mission systems architecture, which allowed for faster and easier software upgrades. This feature made the aircraft highly adaptable to new technologies. A major software update known as Release 4 was in its final testing phase. If everything proceeded as planned, the update would be available for the entire F-22 fleet by the end of the spring. He also pointed out that this upgrade would make it easier to integrate third-party applications into the aircraft's mission systems, enhancing its capabilities even further. When discussing the timeline for the Raptor's new sensor capabilities, Mike mentioned that they were expected to be delivered to the fleet within the next few years. In the meantime, he highlighted that the F-22 remained in high demand. It was also revealed that Lockheed Martin had been supporting increased operations and deployments despite the relatively small size of the F-22 fleet. He acknowledged the challenges of maintaining a fleet that had accumulated over 500,000 flying hours, but reassured that the aircraft would not require major structural upgrades to continue serving well into the 2040s. The long-term future of the F-22, however, remained tied to the Air Force's next-generation air dominance program. Originally designed to replace the Raptor, NGAD had undergone a detailed review the previous year. It was suggested that the analysis appeared to favor continuing the program as planned, although concerns about affordability persisted. Developing a next-generation fighter required significant funding, which had to be balanced with other military priorities, such as stealth refueling tankers and AI-powered drone wingmen, known as collaborative combat aircraft. Additionally, rising costs in the Sentinel intercontinental ballistic missile program had forced the Air Force to reassess its budget. Shoemaker also mentioned that discussions were still ongoing regarding the optimal size of the B-21 Raider stealth bomber fleet. Meanwhile, the Department of Defense was facing potential budget cuts to existing programs in order to redirect resources toward new priorities, including the Golden Dome missile defense system. Despite these uncertainties, Lockheed Martin remained confident in the F-22's continued importance. It was indicated that the aircraft's upgrades were already contributing to NGAD research, ensuring its relevance in modern air combat. However, as the U.S. Air Force moves forward with the next generation of fighters, a major shift is underway. The recent unveiling of the F-47, the Air Force's newest jet, marks a significant leap beyond the F-22, offering superior range, stealth, and cost-effectiveness. Air Force Chief of Staff General David W. Alvin, who spoke at a high-profile event alongside former President Donald Trump, revealed new details about this once-secret aircraft. Alvin reportedly stated that, despite claims from adversaries, the F-47 would be the first crewed sixth-generation fighter in the world. His comments were seen as a response to China, which had recently unveiled its own stealth aircraft. He explained that the F-47 would join the B-21 Raider stealth bomber in the Air Force's new fleet and would be equipped with advanced stealth technology, next-generation sensors, and long-range attack capabilities. These features, he noted, would make the aircraft highly effective in contested battle zones. Although the Air Force did not reveal all details about the F-47, the concept images released showed notable design differences compared to previous fifth-generation fighters like the F-22 and F-35. Observers noted that while the F-47 had a traditional, stealthy nose and bubble canopy, it also included forward canards and sharply angled wings, features not commonly associated with stealth aircraft. Alvin reportedly emphasized that the F-47 would have a significantly longer range than the F-22. The existing F-22 could fly more than 1,850 miles with external fuel tanks before needing to refuel, but the F-47 was expected to exceed that distance considerably. Discussions within the Air Force had suggested the possibility of producing two variants of the aircraft, one larger version designed for long-range missions, particularly in the Pacific, and another smaller version optimized for shorter-range operations in Europe. According to the Air Force, the F-47 represents a major leap forward and had been designed with a modular system that would allow it to be upgraded over time. Officials expressed confidence that this approach would ensure the aircraft remained effective for decades. Alvin further explained that for the past 5 years, the Air Force had been testing NGAD technologies using experimental X-planes. These test aircraft had flown hundreds of hours, helping engineers refine advanced systems and accelerate the development process. He stated that this extensive testing had allowed them to push the limits of technology and bring the fighter into service more quickly than previous programs. He also reportedly expressed confidence that the F-47 would be operational within former President Trump's administration, which would last until January 2029. Comparisons were made to the F-22, which took 6 years to progress from selection in 1991 to its first production flight. It was also noted that references to NGAD test flights had surfaced as early as 2020. However, former Air Force Secretary Frank Kendall had later revealed that prototype flights had likely taken place even earlier, possibly in the mid-2010s. One of the biggest issues with the F-22 was its cost. While the basic construction of each jet cost around $140 million, once research, development, and other expenses were included, the price soared to about $350 million per aircraft. Now, with the Next Generation Air Dominance program, the Air Force plans to field between 220 and 250 advanced fighters. The F-47, a product of this effort, is expected to be a game-changer. Unlike older stealth aircraft, which required extensive maintenance to keep their radar-evading surfaces intact, the F-47 will feature a more durable design, reducing downtime and making it combat-ready more often. This design philosophy follows lessons learned from the new B-21 Raider bomber, which was built to fly frequently without excessive maintenance. The F-47 is also built for adaptability. Thanks to digital engineering and an open systems approach, its software, sensors, and mission equipment can be upgraded quickly and easily. It will also need fewer crew members and ground support to operate, making it more flexible in real-world missions. Boeing won the contract to develop the F-47, which will now enter its engineering and testing phase. Initially, a small number of test aircraft will be produced, with options for further production later. Boeing stated that this fighter will continue its legacy of building some of the most famous aircraft in U.S. history, including the P-51 Mustang, F-15 Eagle, and F/A-18 Hornet. The decision to select Boeing over Lockheed Martin was surprising to some. Boeing has faced issues with several military projects, such as the KC-46 tanker and T-7 trainer, resulting in significant cost overruns. Meanwhile, Lockheed, the maker of the F-22 and F-35, has struggled with delays in upgrading the F-35's technology and managing its high maintenance costs. However, the Air Force has not publicly shared the reasons behind its choice. Despite the debates surrounding the selection process, the Air Force remains focused on ensuring air superiority. The next-generation fighter is expected to dominate the skies, keeping the U.S. ahead of threats for decades. Meanwhile, the F-22 will remain a key part of the USF's fleet, benefiting from upgrades until its eventual replacement by the Boeing F-47, ensuring continued air superiority well into the future. The U.S. Air Force has tried to retire the Warthog for years, but it is still flying combat missions today. Built in the 1970s, the Fairchild Republic A-10 Thunderbolt II is still flying combat missions in one of the most dangerous regions in the world, tracking fast-moving threats in the Strait of Hormuz. So how does a 50-year-old warplane stay relevant in the age of stealth jets and hypersonic weapons? And what is it doing today that modern fighters still can't replicate? Join us as we reveal why the Warthog refuses to disappear and how Iran is currently paying the price for that. Let us start with the sound, one of the things the Warthog is famous for. When an A-10 fires its cannon, the noise it makes sounds like the sky is tearing open. A deep, violent, mechanical roar that lasts less than 2 seconds but feels like it goes on forever. Pilots who have heard it from the cockpit describe it as unlike anything else in aviation. Ground troops who have heard it from below describe something closer to relief, the particular kind of relief that comes from knowing that whatever was about to harm you is no longer a threat. That sound is the GAU-8 Avenger, a 30mm rotary cannon that is not just a weapon mounted on an aircraft. It is the reason the aircraft exists in the first place. The A-10's entire airframe was designed around the GAU-8. The aircraft was built to carry that gun into battle, and every other design decision, the engines, the wings, the cockpit, and the landing gear were made in service of that central function. The GAU-8 fires at a rate of 3,900 rounds per minute. Its average recoil force is 10,000 pounds, which is slightly more than the thrust output of each of the A-10's 2 engines. The rounds it fires are accurate enough to put 80% of shots within a 40-foot diameter circle from 4,000 feet while the aircraft is in flight. In a world that increasingly debates whether human pilots are even necessary, where the conversation is dominated by stealth, hypersonics, and artificial intelligence, the A-10 is the most stubbornly analog weapon in the American arsenal. It flies low and slow. It gets close to things and shoots them with a cannon until they stop being a threat. That is not a philosophy that fits neatly into a PowerPoint about 6th-generation air dominance. But it turns out that philosophy is devastatingly effective in the specific conditions where Iran decided to pick a fight. To understand why the Warthog is in the Middle East right now, let's go back to the beginning and understand what this aircraft was actually built to do. The A-10 was born from a very specific fear. In the 1960s and 70s, American military planners looked at the Soviet Union's massive tank force and asked a deeply uncomfortable question. If the Red Army rolls into Western Europe, what stops it? The answer they arrived at was an aircraft designed from scratch to destroy armored vehicles as quickly and as cheaply as possible, in the most dangerous conditions imaginable, and then come home. The result was an aircraft with a titanium-armored cockpit nicknamed the Bathtub, redundant flight systems designed so the aircraft could continue flying after taking significant damage, and an airframe robust enough to return to base with one engine destroyed, one tail damaged, or significant wing damage. The Warthog was built to survive being hit and keep fighting anyway. During Desert Storm alone, A-10s destroyed over 900 Iraqi tanks, around 2,000 military vehicles, and nearly 1,200 artillery systems. It even reportedly shot down 2 Iraqi helicopters, a rare feat for a ground attack aircraft that carries no radar and was never intended for air-to-air combat. After Desert Storm came Kosovo, then Afghanistan, then Iraq again, then Libya, then Syria. Every time the military establishment declared the Warthog obsolete, another conflict arose in which it proved to be exactly the right tool for exactly the right job. The Air Force, for its part, has been trying to retire the A-10 for years. The argument is straightforward and not without merit. The aircraft is slow and non-stealthy, built for low-altitude attacks that become genuinely dangerous against modern air defenses, equipped with man-portable missiles and radar-guided guns. Advanced air defense systems from Russia and China can engage it long before it reaches its target. The Air Force argues that modern multi-role fighters equipped with precision-guided munitions can perform close air support from safer altitudes, and that the money spent maintaining an aging fleet of specialized aircraft would be better directed toward next-generation capabilities. The Air Force's fiscal year 2026 budget included a request for $57 million to retire all 162 remaining A-10s, 2 years ahead of schedule. The plan was clear. The Warthog was done. However, the Congress disagreed again. The fiscal year 2026 National Defense Authorization Act prohibited the Air Force from reducing the A-10 inventory below 103 aircraft and required at least 93 primary mission aircraft through September 30th, 2026. Any further reduction required a unit-by-unit waiver process, a 30-day notification period, and a multi-year transition plan covering 2027 through 2029, mandated by March 31st, 2026. Congress essentially looked at the Air Force's retirement plan and said no. Keep the Warthog flying. And then, less than 3 months later, Operation Epic Fury began, and the aircraft that was supposed to be in the process of being retired found itself in the opening wave of the largest American military campaign in the Middle East in over 2 decades. U.S. Central Command confirmed that a 10 Thunderbolt II aircraft were employed during the first 48 hours of Operation Epic Fury against Iranian targets, integrated into the initial strike wave from the very beginning of the campaign, not called in as backup, not deployed as an afterthought, in the opening salvos. The first official images CENTCOM released of the A-10 in action during Epic Fury told a story about the variety of threats it was being sent to handle. The aircraft were carrying a mixed loadout: AGM-65 Maverick air-to-surface guided missiles, LAU-131 rocket pods loaded with laser-guided rockets, AIM-9 Sidewinder air-to-air missiles for self-defense, a Lightning targeting pod for precision identification of targets, and a 600-gallon external fuel tank for extended loiter time. That loadout tells you something important about the threat environment in Epic Fury. The Maverick missiles are for armored targets and hardened positions. The laser-guided rockets are versatile precision weapons that can engage small, fast-moving threats at relatively low cost. The Sidewinders suggest the possibility of engaging Iranian drones in the air, which have become a significant threat across the region. And the 600-gallon fuel tank says that whoever loaded this aircraft expected it to stay airborne over the target area for a long time, ready to respond to whatever emerged. CENTCOM emphasized precisely this capability in the statement accompanying the A-10 imagery. The aircraft can remain on station for hours, standing ready to execute a mission whenever needed. That word, loiter, is the one that appears again and again in every discussion of why the A-10 remains relevant. Multi-role fighters can deliver more sophisticated weapons from greater distances, but they cannot circle over a target area for hours at a time, watching for threats to emerge, waiting for a boat to appear around a headland or a missile-launch team to move positions. The A-10 can, and in the geography of the Strait of Hormuz, that capability proved decisive. Chairman of the Joint Chiefs of Staff General Dan Kane confirmed at a Pentagon press conference that the A-10 Warthog is now engaged across the southern flank of Operation Epic Fury, hunting and killing fast-attack watercraft in the Strait of Hormuz. The Strait of Hormuz is one of the most strategically important bodies of water on Earth. Roughly 20% of the world's daily oil supply transits the strait. Iran has long maintained a strategy of threatening to close the strait to shipping in any serious conflict, using swarms of fast attack boats, mines, and coastal missiles to make passage too dangerous for commercial vessels. It is an asymmetric threat that does not require Iran to defeat the U.S. Navy in a conventional sense. It just needs to make insurance companies decide that sending tankers through the strait is too risky. The economic disruption that follows can be devastating for regional states, for global energy markets, and for any American effort to sustain regional alliances. Iran's fast attack boat strategy is built on numbers and speed, Small, fast vessels, difficult to track, appearing from coastal inlets and islands, capable of laying mines or firing missiles before air defense systems can respond effectively. Against an F-35 operating at altitude, these boats are genuinely hard to engage. They are fast, small, low on the water, and easy to lose against the radar clutter of a busy coastline. Against an A-10 flying low and slow at 300 knots with a targeting pod, a Maverick missile, and a pilot who has been training for exactly this scenario for years, they are not hard to find at all. The A-10 was specifically trained for the maritime role of hunting Iran's fast boat fleets long before Operation Epic Fury began. In early February 2026, A-10s were conducting close air support missions for the USS Santa Barbara in the Arabian Gulf as part of the force buildup ahead of the campaign, protecting mine-hunting operations in constrained waters near the strait from fast boat swarms and mining threats. In a March 16th video, CENTCOM Commander Admiral Brad Cooper stated that U.S. forces had destroyed more than 100 Iranian naval vessels and vowed to continue rapidly depleting Iran's ability to threaten freedom of navigation in and around the Strait of Hormuz. 100 vessels. And the A-10 was actively contributing to that tally, not as a supplementary platform, but as one of the primary tools the U.S. military chose to clear the strait. A-10s were also spotted with Sidewinder missiles engaging Shahed-type Iranian drones during counter-unmanned aerial systems missions, an air-to-air role that nobody designed the Warthog for, but which pilots have adapted to over years of operational deployment in environments flooded with cheap Iranian drones. As the campaign expanded, flight tracking data revealed that the Air Force was preparing to send additional A-10s across the Atlantic toward the Middle East, with 12 aircraft arriving at RAF Lakenheath in late March 2026, suggesting a significant expansion of the Warthog's role in the campaign. The aircraft that the Air Force was actively trying to retire 6 months earlier was being reinforced mid-conflict. The debate about the A-10's future will continue after Epic Fury ends, but right now, somewhere over the Strait of Hormuz, an aircraft designed in the 70s to kill Soviet tanks is flying low over contested waters, scanning for Iranian fast boats, and making the Islamic Revolutionary Guard Corps pay for the mistake of thinking that cheap, swarming naval tactics could close the world's most important oil choke point without consequence. Dozens of contacts, all moving fast, all closing on the same point. That's what the radar picture looks like when an Iranian drone swarm is inbound. Not one threat, not two, but a wall of cheap flying machines coming from multiple directions at once, each one designed to make sure the ship in front of them runs out of ways to fight back. 5 years ago, that was a real problem with no clean answer. Today, it isn't. Because somewhere in that engagement, a beam of focused light starts working through the swarm one drone at a time, and the drones just stop flying. No warning, no explosion at range. They just fall. Iran built its entire naval harassment strategy around a vulnerability that no longer exists. And that's the story we're getting into right now. Why Iran built a drone swarm strategy in the first place. To understand why this matters, you have to start with Iran's actual military situation, because Iran didn't build a drone swarm strategy because it wanted to. It built one because it had no other choice. Iran can't fight the US Navy head-to-head. That's not an opinion, it's just arithmetic. A US carrier strike group carries more air power than most countries' entire air forces. Iran's surface fleet is aging, its air force runs on decades-old American hardware, it can no longer get parts for, and its Navy doesn't have the blue water capability to project force beyond the Gulf. Conventional confrontation with the US would end badly and quickly, so Iran went a different direction. Instead of trying to match American capability dollar for dollar, they built a strategy around volume and cost. Send enough cheap things at a problem, and eventually the problem runs out of expensive solutions. The Shahed series drones are the heart of that approach. They're not sophisticated. They fly slow, they're relatively easy to detect on radar, and they don't have the kind of electronics you'd find on a military aircraft. What they have is price. A Shahed 136 costs somewhere in the range of $20,000 to $50,000 to produce. A standard missile intercept costs over $2 million. Send 20 drones at a ship and force it to fire 20 missiles, and you've just burned through $40 million worth of the enemy's inventory for under $1 million of your own. That's a trade Iran wins every time. And the strategy had real teeth. In 2019, drone and cruise missile strikes hit the Saudi Aramco processing facilities at Abqaiq and Khurais, knocking out roughly 5% of global oil supply overnight. The attack, in which U.S. officials linked to Iranian hardware, showed the world that this wasn't theory. Cheap aerial munitions could reach high-value targets and cause serious damage before anyone could stop them. In the Red Sea, Houthi forces backed by Iranian weapons and training ran the same playbook against commercial shipping and U.S. Navy warships for months. The USS Carney alone fired over 100 interceptor missiles in a single deployment period, defending against drone and missile attacks. 100 missiles. Gone. At sea, you can't just reload. A ship carries what it carries, and once the magazine runs low, the options get thin fast. That's the vulnerability Iran was targeting. Not the armor, not the sensors, not the crew, the inventory. Western navies are built around expensive precision weapons that you can only carry so many of, and Iran was betting it could keep sending cheap drones until those weapons ran out. For a while, the bet looked reasonable. Then the U.S. Navy started putting a very different kind of weapon on its ships. What the U.S. Navy's laser weapons actually are. The system the U.S. Navy has been quietly putting on its surface ships is called Helios. High-energy laser with integrated optical dazzler and surveillance. USS Preble was the first destroyer to receive it, making her the first operational U.S. surface combatant to carry a solid-state laser weapon. Not a prototype sitting in a lab, not a test rig on a barge, a combat-ready system mounted on a warship operating in real threat environments. The physics behind it are simpler than you might expect. Helios focuses a high-powered beam of light onto a target and holds it there. The energy transfers into the surface material as heat, and it keeps building until something fails. The airframe warps, the engine seizes, the fuel ignites, or the electronics fry. There's no warhead, no shrapnel, no projectile traveling downrange. Just a sustained column of thermal energy moving at the speed of light, delivered precisely where the fire control system points it. What that means in practical terms is a cost per shot figure that sounds made up until you look at how the system actually works. Each firing costs roughly $1 in electricity. That's it. Compare that to the missile intercept costs we already covered, and you start to see why the Pentagon kept pushing this program even when early versions underperformed. The magazine situation is what really separates this from every other weapon on the ship. As long as the ship's power generators are running, the laser can keep firing. There's no reload, no resupply run, no hard limit on engagements per sortie. In a prolonged drone harassment campaign, exactly the kind Iran has been running in the Gulf, that's not a minor advantage. It's a structural one. Helios also isn't a single-mode weapon. At lower power settings, the dazzler function can blind the optical sensors on a surveillance drone without destroying it. Useful when the rules of engagement require a measured response. Step up the power and you can disable propulsion systems or cook the electronics without the airframe coming apart. Go to full power and you're burning through the drone itself. The operator picks the effect, the system delivers it. Before Helios, the Navy was already fielding a lower power version called Odin, Optical Dazzling Interdictor, Navy. Odin went on multiple surface ships first, which gave the service real operational data on how directed energy performs outside a test range. Humidity, sea spray, atmospheric turbulence, all of it affects how a laser beam holds together over distance, and you can't simulate that in a lab. Odin gave the Navy years of that data before Helios ever went to sea. The limitations are real and worth stating plainly. Heavy rain or thick fog degrades beam quality significantly because the atmosphere scatters the energy before it reaches the target. The system also needs to hold its beam on a target for several seconds to achieve a kill, which means a target that's maneuvering hard at long range is harder to engage reliably. Against a supersonic anti-ship missile pulling high G turns, a laser at current power levels isn't your first line of defense. But slow, straight-flying drones on a fixed approach path? The dwell requirement barely matters. A Shahed flying a pre-programmed route at low altitude isn't doing anything to break the beam's lock. It's just flying in a straight line toward a ship that's now pointing something at it that doesn't miss and doesn't run out of ammunition. The encounter, laser versus drone swarm. Picture the scenario the US Navy has been wargaming for years. A destroyer operating in the Persian Gulf, well inside the range corridor Iran uses for its drone operations. The radar picture fills with contacts. Not one or two, but a coordinated wave coming in from multiple bearings at once. Some are high, some are skimming low over the water to complicate the tracking picture. This is the swarm profile Iran has rehearsed, and it's specifically designed to split a ship's defensive attention across too many targets simultaneously. Against a traditional layered defense, this is where things get ugly fast. The Phalanx close-in weapons system can engage incoming threats, but it covers a limited arc, burns through its 20mm ammunition quickly, and by the time drones are close enough for Phalanx to reliably engage them, you're already in a bad position. Standard missiles are accurate, but as we covered, there aren't unlimited rounds on board, and they're wasted on a $20,000 drone. Electronic jamming works against drones that rely on GPS or radio command links, but Shahed-type systems fly pre-programmed routes, cut the signal, and they just keep going. None of the traditional answers solve the volume problem cleanly. Helios approaches the same problem differently. The fire control system pulls track data from the ship's radar, assigns priority to the targets posing the most immediate threat, and the beam slews onto the first contact. Slew, dwell, kill, move. The mechanical turret repositions fast enough that the transition between targets takes a fraction of a second. There's no reload cycle between engagements, no cooldown that a swarm operator could try to exploit. The system works through the contacts sequentially, and the engagement rate is measured in seconds per drone, not minutes. The actual kill mechanism depends on where the beam holds. On a drone with a combustion engine, sustained heat on the fuel system or exhaust components can trigger ignition. On an electric UAV, the beam cooking through the fuselage reaches the battery pack or motor controller, and that's the end of the flight. Either way, the drone doesn't explode dramatically at distance. It just stops flying and drops. Sometimes there's a small fire on the way down. Mostly it just falls. That last detail is something Iran's planners didn't fully account for, and it matters operationally. When a missile intercept happens, both sides know. There's a detonation, a debris field, a visible event that tells the attacking force its drone was stopped. The swarm operators can count intercepts, adjust, and keep pushing. With a laser kill, the feedback loop breaks down. A drone goes offline and the operators have no immediate way to know why. Signal failure, mechanical fault, or something they can't see burning through the airframe from 12 kilometers away. The swarm starts thinning, and the people who launched it don't have a clear picture of what's stopping it. US Navy testing has demonstrated exactly this capability against drone targets under operational conditions, and the service has publicly confirmed Helios is deployed and functional. The Red Sea operations didn't just validate the threat picture, they put directed energy systems into a genuine combat environment for the first time, generating data on real-world performance that no test range can replicate. What Iran's operators would actually experience on the receiving end of a Helios engagement is a swarm that starts losing units with no obvious cause. No contrails, no explosion at range, no radio intercept of a missile launch command. Just drones going silent, one after another, while the ship they were sent to overwhelm keeps sailing. The swarm thins, the attack fails, and somewhere in an Iranian operations room, someone's trying to figure out what just happened to their strategy. What this means for Iran's strategy going forward. The math Iran built its doctrine on has flipped completely. A dollar defeating a $20,000 drone isn't a minor economic inconvenience. It's the entire logic of the swarm strategy running in reverse. Iran needed the cost exchange to work in its favor, and now it doesn't. So what does Iran do next? There are a few options on paper, and none of them are good. The first is speed. If a laser needs several seconds of dwell time to achieve a kill, then a faster drone reduces the window the beam has to work with. In theory, you could build drones that cross the engagement zone quickly enough to limit damage. In practice, faster drones cost more to produce, require better propulsion systems, and burn more fuel, which cuts range. The whole point of the Shahed approach was disposable cheapness. The moment you start engineering for laser resistance, you're spending more per unit, which means you need fewer of them, which means the swarm gets smaller, which means the saturation strategy stops working. Reflective coatings are the other idea that gets floated. Certain materials can deflect or disperse laser energy rather than absorbing it. So coat the drone's surface, and maybe you reduce the beam's effectiveness. The problem is that materials capable of reflecting the specific wavelengths, military lasers operate at add weight, add cost, and require manufacturing precision that a mass production drone facility isn't set up for. You've turned a cheap, expendable weapon into an expensive, specialized one. And you've still only bought a few extra seconds of dwell time, not immunity. The saturation angle is the only one with any real logic to it. If you can't make each drone harder to kill, send enough of them that the laser can't work through the whole swarm before some get through. To do that, you need to know the system's maximum engagement rate, how many drones per minute it can cycle through, and then exceed it by a wide enough margin that some survive. The engagement rate for Helios is not public information. Iran would be building toward a number it can't verify, spending money on drone production at a scale that starts to undermine the cost advantage that made the strategy viable in the first place. Every Iranian naval commander and IRGC planner operating in the Gulf now has to factor in that any U.S. Navy destroyer they're looking at might be carrying a weapon with an effectively unlimited magazine. That changes targeting calculus, risk tolerance, and the whole harassment playbook Iran has been running for years. There's an irony buried in all of this that's worth sitting with. Iran's persistent drone pressure in the Gulf and the Red Sea, the harassment, the Houthi campaigns, the cost exchange problem that had Western navies genuinely worried. That pressure is a big part of why the U.S. moved so fast to get directed energy systems operational. Iran kept poking at the vulnerability, and the U.S. responded by closing it. The aggression that was supposed to stress American naval capacity may have done more to accelerate American laser development than any Pentagon budget cycle would have on its own. Iran spent years building a strategy around a math problem it thought the U.S. couldn't afford to fix. Then the U.S. fixed it for roughly $1 a shot. The U.S. military just crossed a red line that has stunned foreign navies. While patrolling the Pacific, a group of sailors spotted something impossible, a secret variant of the A-10 Warthog, flying low, fast, and armed with weapons no one's ever seen before. This wasn't a training flight, it was a silent warning. What is this mystery aircraft doing over the ocean? And why is the Pentagon refusing to comment? Join us as we uncover the truth behind the secret Super A-10 spotted above the Pacific. On December 6, 2024, 4 A-10 Thunderbolt II aircraft were seen flying toward Clark Air Base in the Philippines. Their presence sparked attention online, prompting the U.S. Air Force to confirm they were part of a joint training mission with the Philippine Air Force through December 16. The A-10, often called the Warthog, is built for war. Armed with a 30mm cannon and up to 16,000 pounds of bombs and missiles, it is designed to destroy tanks and even armored targets. It has also proven capable of striking small ships in recent years, showing its growing role in maritime operations. This deployment followed the sighting of nearly 100 Chinese vessels near Thitu Island, a territory held by the Philippines. The island sits in the South China Sea, a region of long-standing territorial disputes. China claims nearly the entire sea, which overlaps with claims from several countries, including the Philippines. These disputes have led to repeated clashes at sea and growing political tension. Since 1951, a mutual defense treaty has linked the U.S. and the Philippines. The agreement states that an attack on either country's aircraft, ships, or armed forces in the Pacific, including the South China Sea, would require both to respond. The A-10s sent to the Philippines came from the 25th Fighter Squadron, South Korea. They were deployed under the U.S. military's Dynamic Force Employment Strategy. This concept focuses on keeping American movements flexible and less predictable while staying focused on long-term goals. This approach keeps rivals uncertain and cautious in today's tense global climate, especially in the Indo-Pacific. The U.S. sees the Indo-Pacific as a critical region. As China grows more powerful, the Pentagon continues to test and improve its readiness. The A-10's arrival marks the second joint air exercise with the Philippines since late November. In the earlier drill, both sides flew fighter jets over the Philippine Sea, showing their cooperation and ability to respond together. The A-10 Thunderbolt II was never built for style or speed. It was built to dominate the ground game. While faster jets often overshoot or struggle with precision strikes, the A-10 excels at low altitude, close quarters combat, cruising at just 350 miles per hour to deliver deadly accuracy where it counts. Every part of its design favors durability and control. Reinforced with a honeycomb structure, the wings are lightweight yet rugged. Its oversized ailerons stretch nearly half the wingspan, giving it impressive agility at low speeds. This lets the Warthog stay locked on targets in tight, low-flying conditions, where precision is everything. Designed to take heavy damage and keep flying, the A-10 is a relentless force overhead, silent, steady, and dependable in the face of ground threats. Despite its battlefield potential, the A-10 wasn't initially embraced. Many pilots viewed it as sluggish and unattractive compared to sleek, high-speed fighters. That perception began to shift in 1987 when the OA-10 was redesignated for forward air control missions, signaling its evolving role. Its first operation came in 1983 during Operation Urgent Fury in Grenada, where it was deployed to support marine landings. No shots were fired, and no enemy aircraft rose to challenge it. Everything changed in 1991 during the Gulf War. 132 A-10s were deployed, and what followed secured the Warthog's legendary status. Along with devastating ground attacks, the A-10 proved it could fight in the air. It took down 2 Iraqi helicopters, including one destroyed by Captain Robert Swain using the GAU-8 Avenger cannon. The war, however, was unforgiving. 4 A-10s were shot down, 11 more were hit and returned to base. 2 were too damaged to be repaired. 1 crash-landed beyond recovery. As losses mounted, commanders reassigned A-10s to lower-risk missions near the southern border. Even then, the Warthog stayed aggressive, precisely targeting Scud launchers and armored units. They flew over 8,100 sorties, launched most of the Mavericks used in the war, and achieved a mission success rate of 95.7%. Calls to replace the A-10 with a modified F-16 soon faded. The Warthog had proven itself and earned its place. The Gulf War wasn't the end of the A-10's relevance. In the mid-1990s, A-10s were deployed to Bosnia during intense unrest. They fired over 10,000 rounds of 30mm ammunition, targeting stolen tanks and artillery held by Bosnian Serb forces. On August 11, 1994, 2 A-10s tracked and destroyed an anti-tank vehicle, leading to the surrender of the remaining stolen weapons. The mission demonstrated how the aircraft's mere presence could shift the battlefield. A year later, during NATO's Operation Deliberate Force, the Warthog returned to combat, neutralizing enemy artillery and fortified positions. Even after the campaign ended, A-10s remained in the skies, deterring any resurgence of hostile activity. In 1999, the A-10 was called into action over Kosovo. Initially tasked with combat search and rescue, it was quickly reassigned to ground attack operations. On April 6th, it launched its first major strike and remained active through the war's final weeks, delivering precise firepower until the campaign concluded in June. The aircraft did not participate in the earliest phase of the Afghanistan invasion in 2001. Its return came in March 2002 when it was deployed to bases in Pakistan and Afghanistan. During Operation Anaconda, A-10s struck Taliban and al-Qaeda fighters entrenched in the mountains. Even after the official operation ended, the Warthog remained in the region, carrying out one of its most extended continuous deployments. Its mission was clear: locate, engage, and eliminate hostile forces in unforgiving terrain. In 2003, the A-10 returned to full-scale war during Operation Iraqi Freedom. 60 Warthogs were launched at the start of the invasion, and their impact was immediate. Missions were conducted with an 85% success rate, reflecting the aircraft's reliability and pilot expertise. A-10s fired over 380,000 rounds of 30mm ammunition and were even used to drop propaganda leaflets to break enemy morale. Despite its toughness, one aircraft was lost near Baghdad International Airport after sustaining heavy fire. By 2007, the A-10 had been upgraded. The new A-10C variant introduced digital targeting systems and modern communication tools. The Maryland Air National Guard was the first to take the upgraded Warthog into combat. These enhancements allowed for faster target acquisition and greater accuracy. Between 2009 and 2012, the A-10 flew up to 34,500 missions annually. Even in 2013, it remained essential in Afghanistan, recording over 11,000 sorties in 6 months. Between 2006 and 2013, the A-10 Warthog flew 19% of all close air support missions in Iraq and Afghanistan, more than the F-15E Strike Eagle and B-1B bomber. Only the F-16 flew more. However, regarding raw firepower delivered at close range, few aircraft matched the Warthog's battlefield impact. Its relevance continued in 2011 during Operation Odyssey Dawn in Libya, where A-10s attacked Libyan ground forces with the same precision they had shown in earlier conflicts. Decades after its introduction, the Warthog remained a dependable and deadly asset in U.S. combat operations. By 2015, the A-10 was once again drawn into a growing conflict. The 122nd Fighter Wing was deployed to the Middle East as ISIS expanded across Iraq. By mid-November, A-10s were conducting near-daily strikes against ISIS targets in central and northwestern Iraq. In just 2 months, the aircraft accounted for 11% of all U.S. Air Force missions in the region, reaffirming its dominance in close air support. Despite its effectiveness, the Air Force had already begun shifting focus to the future. Military planners deemed the A-10 outdated and pushed for its retirement, reallocating $4.2 billion to the F-35 Lightning II, a stealth, multi-role fighter. But the decision sparked a fierce debate in Washington. Congress quickly intervened. Many lawmakers, aware of the A-10's battlefield value, demanded that any replacement match its performance. The Air Force could not proceed with retirement unless the F-35 proved equally capable in real-world combat. Instead of being retired, the A-10 was upgraded. Congress blocked its phase-out and ordered enhancements to extend its operational life. It forced the military to improve a platform it had planned to abandon, fueling ongoing debate about the future of close air support. Then on November 15, 2015, just 2 days after the Paris terrorist attacks, A-10s returned to combat. In coordination with AC-130 gunships, they launched a decisive strike in Syria, destroying over 100 ISIS-controlled oil tankers. The mission, named Tidal Wave 2, aimed to dismantle ISIS's oil smuggling network and sever one of its main sources of revenue. Unlike the failed World War II raid it was named after, this time the mission succeeded. Though the A-10 earned its reputation as one of the most lethal ground attack aircraft ever built, its history is marked by controversy. On December 8, 1988, tragedy struck in Remscheid, West Germany, when an A-10A lost control in poor weather and crashed into an apartment building. The pilot and 6 civilians were killed, and 50 others were injured. Investigators blamed disorientation due to low visibility, but years later, a sharp rise in cancer rates reignited fears that the aircraft may have carried depleted uranium rounds, despite official denials. Nearly a decade later, a more baffling incident occurred. On April 2, 1999, Captain Craig D. Button veered hundreds of miles off course during a routine flight from Davis-Monthan Air Force Base. He ignored all radio contact, never attempted to eject, and ultimately crashed into a remote Colorado mountainside. The crash was ruled a suicide, but more profound questions emerged. Button's aircraft carried live bombs that were never recovered. Then on March 28, 2003, during the Iraq War, British troops came under friendly fire from A-10s. Lance Corporal Matty Hull was killed, and 5 others were wounded. The incident drew harsh scrutiny over the aircraft's targeting systems and the risks of miscommunication during close air support. The A-10's combat record in Afghanistan also faced criticism between 2010 and 2017. It was linked to more civilian casualties than any other U.S. aircraft and was involved in multiple friendly fire events, including one that killed 10 American troops. These incidents raised tough questions about the aircraft's place in modern warfare. Yet despite its flaws, the A-10's effectiveness was never in doubt. Its ability to deliver sustained, precise firepower and survive heavy damage kept it indispensable to commanders on the ground. By 2026, efforts to retire the Warthog had stalled. Congressional pushback, growing global tensions, and delays in the F-35 program forced the Pentagon to rethink. Retirement plans were shelved, political support surged, and battlefield performance proved there was still no equal. The aircraft's evolution reached a new phase with the Suite 8 upgrade package. Among its standout features was the V-12 airborne recovery system, significantly improving coordination between pilots, special forces, and downed air crews. This upgrade enhanced the A-10's precision and broadened its mission scope into rescue operations. But the true breakthrough came with its new standoff capabilities. Outfitted with long-range guided munitions, the A-10 no longer had to fly dangerously close to enemy fire. It could deliver devastating strikes from a distance, shifting from a low-altitude brawler to a long-range enforcer, changing how the Warthog waged war. In parallel, the A-10 Warthog underwent a major leap in night warfare capabilities. With the integration of advanced night vision systems, it could now operate effectively at low altitudes in total darkness. Coupled with faster-loading AGR-20 precision rockets, it delivered faster, deadlier strikes, reshaping battlefield timelines and tempo. Then came Suite 9, bringing even more powerful upgrades. A new situational awareness pad enabled seamless digital coordination with ground forces. Joint terminal attack controllers could now relay exact coordinates electronically, eliminating the need for voice commands or visual signals. This dramatically improved mission precision. Target verification systems were also added to reduce friendly fire. The system added a critical safety layer in combat by automatically cross-checking coordinates and target profiles before each strike. Meanwhile, multi-target capabilities allowed the Warthog to engage up to 6 threats simultaneously, using munitions ranging from 500-pound bombs to 2,000-pound JDAMs, selected based on mission needs. Pilots received Hobbit helmets with real-time head tracking, enabling weapons to be guided simply by looking at a target. This reduced reaction time and increased accuracy in fast-paced combat. The A-10 had transformed. No longer just a Cold War tank buster, it became a modern, tech-equipped battlefield asset, capable of operating in remote, unpredictable war zones with minimal support. Still, its future remained uncertain. Congress demanded proof that upgrades made the Warthog superior to its intended replacement, the F-35. But when a head-to-head test was scheduled, the Air Force wasn't eager for transparency. Rumors spread that the trial was biased in the F-35's favor. Most of the results were hidden. No public footage, no definitive answers, just silence, fueling suspicion. The sleek and stealthy F-35 was built for high-speed, deep-penetration strikes, not close air support. It couldn't loiter low and slow over ground troops like the Warthog. And that was the issue. Close air support demands toughness and proximity, flying low, absorbing fire, and striking back instantly. That was the Warthog's domain. Its titanium bathtub cockpit protected pilots, who often flew low enough to see the fight unfold in real time. Despite its unmatched capabilities, the Air Force continued pushing to retire it, driven largely by budget politics. The F-35 was a $400 billion mega project. Admitting it couldn't replace the A-10 was politically and financially challenging. But the Warthog wasn't finished. Suite 10 marked the most dramatic upgrade in its history. It now carried AGR-20 rockets, JDAM kits for precision bombing, and small-diameter bombs for multi-target runs. Theoretically, a single A-10 could destroy up to 18 enemy positions in one pass, each with a different weapon. That wasn't all. A synthetic aperture radar gave the Warthog hunters vision, able to track and lock onto targets through smoke, fog, or darkness with lethal clarity. Boeing followed up with a massive hardware overhaul, delivering 173 new wing sets rated for 20,000 flight hours each. The Air Force added another 112 through the ATAC program, securing the A-10's place in the skies for years to come. But the transformation didn't stop there. A cutting-edge data link system was installed, allowing A-10s to share real-time battlefield intelligence, dramatically improving coordination and target engagement. The Warthog was no longer just relevant, it was more lethal, aware, and adaptable than ever. At Eglin Air Force Base, the next leap came with a project called Suite 10. This wasn't routine maintenance, it was a full-scale digital modernization. Using agile development, Upgrades were delivered faster to meet the demands of modern combat. Suite 11 introduced major enhancements: jam-resistant GPS, a next-gen ARC-210 radio, immersive 3D audio, and an 11.6-inch high-res digital display. Central to it all was a revamped cockpit interface, replacing analog dials with intuitive digital systems that gave pilots sharper visuals and more precise control, marking the A-10's most significant interior overhaul since 2005. With its systems transformed and its battlefield credibility restored, the Warthog returned to action. In January 2018, 12 A-10s thundered into Kandahar, Afghanistan, with a clear mission: eliminate enemy forces with the precision and brutality the aircraft was built for. During the 2022 Russian invasion of Ukraine, Kyiv requested 100 surplus A-10s, confident in the jet's tank-killing power, but the Pentagon declined, citing the aircraft's slower speed and vulnerability to advance Russian air defenses. Still, the Warthog remained active. By late 2024, it was flying missions over Syria. Enemy vehicles, mortar positions, and even a Soviet T-64 tank were destroyed with devastating firepower. On December 8th, as the Assad regime crumbled, A-10s joined B-52s and Fa-15Es in a sweeping bombing campaign that neutralized over 75 ISIS strongholds in days, denying the group any chance at resurgence. If the U.S. were to greenlight A-10 Warthog attack missions in the South China Sea, it would ignite one of the most intriguing military showdowns of the modern era. While many would instinctively scoff at the A-10's chances against China's modern air fleet, especially sleek, fast fighters like the Chengdu J-10C, Shenyang J-16, or even the stealthy J-20 Mighty Dragon, that underestimation might be premature. In a tightly coordinated U.S. air campaign with proper escort from F-15s, F-16s, or stealthy F-35s, the A-10 becomes a surgical instrument of destruction, and the skies over the South China Sea would become a theater of extremes. It wouldn't be a clean sweep for either side. China might flex air superiority, but the Warthog would leave a scar on the battlefield. The ultimate clash wouldn't be decided in air duels alone. It would hinge on how long the A-10s could survive and how much devastation they could unleash before they were forced back. And history has shown, counting the Warthog out too early has always been a mistake. In an era dominated by stealth fighters and AI-driven warfare, this rugged, titanium-armored beast still earns its place, not as a relic of the past, but as a relentless force in the present. For years, the Pentagon kept trying to kill it. Too slow, they said. Too vulnerable. A relic of a Cold War that ended before most of its pilots were born. And then Iran happened. One A-10 down. Enemy forces closing in on the crash site. Rescue helicopters inbound with a 20-minute window to work with. The Warthog that showed up to hold that window open wasn't the aircraft anyone remembered from Desert Storm footage. It was something else entirely. How does a 50-year-old airframe become the most feared close air support platform over Iran in 2026? That's what we're going to answer. The Air Force wanted the A-10 gone for a long time. The argument wasn't complicated. The jet was designed in the late 1960s and early 1970s to stop Soviet tank columns pouring through the Fulda Gap in Germany. That threat disappeared in 1991. So why were they still flying a purpose-built tank killer decades later when the tanks were gone and the threat environment had completely changed? Budget pressure made the case louder. Through the 2010s and into the early 2020s, the Air Force repeatedly tried to retire the fleet and redirect that money toward a F-35 procurement. The logic was clean on paper. The F-35 is multi-role, survivable against modern air defenses, and stealthy in ways the A-10 never could be. Why keep a single mission, slow-moving jet when you could have one aircraft that does everything? Congress kept saying no, and so did the combat commanders who actually called in air support. The reason wasn't nostalgia, it was math. The A-10 could stay over a target area for hours in ways that fast movers simply couldn't sustain. When a ground unit needed a jet circling overhead for 90 minutes while a situation developed, the F-35 wasn't the answer. The A-10 was. And when it did take fire, it had a better chance of bringing its pilot home than almost anything else flying. The cockpit sits inside a titanium tub that absorbs hits that would destroy a conventional airframe. The hydraulic systems are fully redundant, meaning the aircraft can fly on mechanical backups if the primary lines get severed. There are confirmed cases of A-10s returning to base with one engine destroyed, a chunk of one wing missing, and the landing gear jammed and still landing safely. That survivability record kept the retirement conversations from ever fully closing. But there was a second argument quietly building in the background, one that didn't get much attention in the budget debates. While the Air Force and Congress fought over whether to retire the A-10, engineers were already rebuilding what it could actually do in a fight. The airframe everyone assumed was obsolete was being rewired, rearmed, and re-equipped for a threat environment its original designers never imagined. The upgrades that changed everything. Start with the gun because everyone does, and then forget about it for a minute. The GAU-8 Avenger cannon is still there. 30 millimeters, 3,900 rounds per minute, the whole legend. But the gun is the part of this aircraft that hasn't changed the fight. What changed the fight is everything wrapped around it. The first piece is the Sniper Advanced Targeting Pod. Before Sniper, the A-10's targeting was limited by what the pilot could see through a basic optical system and whatever a ground controller could talk them onto. Sniper changed the geometry of the whole engagement. It gives the aircraft a high-resolution infrared and electro-optical sensor that can identify a specific vehicle, read a license plate, or distinguish a weapons cache from a supply truck at ranges so far out that ground-based radar and manpads crews don't even know an aircraft is in the area. The A-10 used to have to get close to see the target. Now it finds the target first, from a distance that keeps it out of the threat envelope entirely. That shift matters more than almost anything else in this upgrade package, because the original knock on the A-10 in a modern threat environment was always the same. It's too slow to survive. Slow is still true, but slow only kills you if you're inside the range where the enemy can engage you. Sniper pushed that boundary out, and the standoff munitions package extended it further. The AGM-65 Maverick was already part of the A-10's loadout, but upgraded variants have increased effective range and added better seeker heads for engaging targets in lower visibility conditions. More importantly, the integration of the small diameter bomb gave the aircraft a glide weapon it can release from altitude, well outside most short-range SAM and manpads coverage, and let the bomb fly itself to the target. The A-10 doesn't have to commit to a low strafing run to kill a vehicle column. It can release from altitude, turn, and be repositioning before the weapons even arrive on target. What standoff actually means for a platform this slow is a complete reversal of the original risk calculation. The A-10 was designed to absorb hits because it had to get close. The upgraded A-10 is designed to never get close in the first place. The titanium tub and the redundant systems are still there as a last resort, but the goal now is to keep the aircraft in a position where none of that survivability hardware needs to be tested. Then there's the electronic warfare layer. The updated ALQ-131 jamming pod doesn't make the A-10 invisible to radar, and it's not trying to. What it does is degrade the quality of the radar picture the enemy is working with, introduce enough noise and uncertainty into a radar-guided system that a lock becomes unreliable, and spoof IR seekers long enough to break their acquisition window. The A-10 isn't stealthy, it's unpredictable, which in a close support environment where the engagement timeline is short, is sometimes more useful. Layer Link 16 integration on top of all of that, and the aircraft is now talking to everything else in the battle space in real time, receiving targeting data from other platforms, updating its own picture continuously, and passing information back to the rescue and strike packages operating alongside it. Taken one at a time, each of these upgrades sounds like an incremental improvement. Put them together and you get an aircraft with completely different threat calculus than the one the Pentagon kept trying to retire. The A-10 that came out the other side of these programs wasn't the same machine that was built to blunt Soviet armor. It was something the threat environment over Iran in 2026 hadn't fully accounted for yet. Iran 2026? The threat environment? Every analyst who looked at Iran's air defense network before the conflict started reached roughly the same conclusion. This was not a place you sent A-10s. The Iranians had spent years building a layered system specifically designed to deny low-altitude access. At the top end, they were operating S-300 derivatives supplied through Russian channels before the sanctions environment tightened, long-range radar-guided systems capable of engaging targets at high altitude and significant distance. Below that sat the domestically produced Bavar 373, Iran's answer to the Patriot system, which had been quietly upgraded through several iterations and covered the mid-altitude band that aircraft would try to use to avoid the lower-tier threats. And at the bottom of the stack, at the altitudes where a slow aircraft conducting close support actually operates, there was dense manpads coverage, shoulder-fired infrared seekers carried by infantry units, vehicle-mounted short-range systems, overlapping fields of fire across the forward areas. The kind of environment where a slow-moving jet at low altitude doesn't get a second chance. The air campaign opened the way these campaigns usually do. F-35s went into the high-threat corridors first, using their low observability and sensor integration to map the network and take down the nodes that made the layered system function. F-15EXS handled the strike packages against hardened targets that required heavier payloads. The A-10s operated in a different lane entirely, assigned to close support in areas where the air defense picture had already been degraded, working with ground forces in zones that were semi-permissive rather than fully contested. That division held through the early weeks. Then the front lines shifted. A pair of A-10s got tasked with a strike near a contested forward position, where the situation on the ground had moved faster than the air defense suppression work had. The area wasn't clean. It was semi-permissive at best, meaning some of the threats were degraded, some weren't, and the manpads coverage was still intact in pockets. The mission called for close support that faster aircraft couldn't provide, with the loiter time the ground commander needed. And the upgraded A-10s were the answer the planners reached for. One of them took a hit on the ingress. A shoulder-fired missile, close range, caught the aircraft before the EW suite could fully break the seeker's acquisition. The pilot got out. The aircraft came down in a zone where enemy ground forces were near enough to reach the crash site before any rescue package could arrive. And with the threat environment still active, the helicopters couldn't go in without suppression. The second A-10 was still airborne, still armed, and now operating alone in an environment that had just proven it could kill aircraft like this one. 20 minutes. That's what the rescue package needed to assemble and get in. What happened in those 20 minutes is the reason the retirement debate looks different now than it did before the conflict started. The recovery mission, the second A-10 pilot didn't climb out of the threat zone. He turned back into it. The sniper pod went to work first. From a distance far enough out to stay below the manpad's engagement envelope, the pilot started building a picture of what was happening on the ground. The downed pilot had survived the ejection and was moving, trying to put distance between himself and the wreckage. Enemy forces were on foot and in vehicles, converging from two directions, and they were moving faster than the rescue helicopters could. The A-10 pilot could see all of this. The ground forces closing in couldn't see him at all. That asymmetry is the whole point of the sensor upgrade. In the original threat calculus, the A-10 announces itself the moment it enters the engagement area, and the enemy has time to react. With Sniper running from standoff range, the pilot spent several minutes mapping exactly where every threat element was, what they were driving, which direction they were moving, and where the downed pilot sat relative to all of it before he ever committed to a weapons run. By the time he started engaging, he already knew the outcome of every shot he was going to take. The EW suite went active next. The ALQ-131 started working against the radar-guided systems in the immediate area, degrading the picture for any crew trying to track and engage the inbound aircraft. Enemy radio communications in the zone started breaking up. The suppression wasn't total, but it didn't need to be. It needed to be good enough to keep the rescue window open long enough for the HH-60Ws to get there. First weapons run targeted the closest enemy element on foot, the group with the best angle on the downed pilot's position. The pilot came in with APKWS laser-guided rockets, not the cannon. The APKWS rounds let him put precision fire on a tight target without the blast radius that would have threatened the pilot on the ground a few hundred meters away. The element stopped moving. Then the vehicles. A column of trucks was pushing up a road toward the crash site from the north, moving fast enough that they'd reach the area before the Jolly Greens arrived. The A-10 pilot pulled back to distance, stepped outside visual range of that column, and fired two AGM-65 Mavericks in sequence. The lead vehicles stopped. The columns stopped with them. Nothing behind the first two trucks had anywhere to go, and nothing behind them tried. The HH-60W Jolly Green 2s came in under the suppression umbrella the A-10 had spent those 20 minutes building. The radar environment was degraded. The two ground threats that had the best shot at the crash site were neutralized. The downed pilot was recovered and on the helicopter before the enemy managed to reorganize a response. When the A-10 landed, the pilot had expended gun rounds, fired two Mavericks, and run the EW suite hard enough that it needed a maintenance check before the next mission. Every single thing that kept that rescue window open traced directly back to the upgrade package. The titanium tub and the redundant hydraulics didn't save anyone that day. The sniper pod, the Mavericks, and the jammer did. The airframe was just the platform carrying the tools that actually mattered. What this means for the A-10's future. The retirement debate didn't end after Iran, but the terms of it shifted in a way that's hard to walk back. What the conflict proved is that there's a specific operational gap the upgraded A-10 fills that nothing else in the inventory covers the same way. The F-35 can't hold a loiter pattern over a dynamic ground situation for the time the A-10 can. Attack helicopters have the loiter capability, but can't absorb the threat levels the upgraded A-10 now operates through. The combination of persistence, standoff precision, and survivability in semi-permissive environments is something the Air Force doesn't have a direct replacement for. The Air Force is now evaluating a further integration package, more sensor capability, expanded munitions compatibility, pulling more data from the Link 16 network. The Warthog isn't being positioned as a replacement for anything newer. It's being kept because it does a specific job at a cost and reliability level that a newer platform can't match, and Iran proved that job is still real. The A-10 was never supposed to make it to 2026, and honestly, the old one didn't. What's flying over Iran is the same airframe carrying a completely different set of answers to a completely different set of threats. Same aircraft, different war.
Germany is no stranger to producing top-of-the-line weapons and ammunition. Their commitment to innovation and engineering excellence has earned them a formidable reputation in the world of military technology. German tanks, in particular, are renowned for their balance of firepower, protection, and mobility. These tanks have been deployed in various conflicts, showcasing their mettle in Afghanistan, the Balkans, and even in peacekeeping exercises during the Cold War. They have proven their worth in real combat situations. Now that some of these German tanks have been sent to Ukraine, how does Russia react? Join us as we explore this deadly German supertank that shocked Russian invaders in Ukraine. Germany's decision to equip Ukraine with deadly supertanks represents a significant boost to Kyiv's defense capabilities in the ongoing conflict against Russian forces. The massive tank, the Leopard 2, is often considered one of the world's best main battle tanks. It hails from Germany, manufactured by the renowned company Krauss-Maffei-Wegmann GmbH. This tank, belonging to the third post-war generation, is operated by a crew of 4. What makes the Leopard 2 stand out are its remarkable features. These include a flawless fire control system, a formidable gun, and robust armor. Astonishingly, despite its considerable weight of around 70 tons, it can reach speeds of up to 72 kilometers per hour and come to a halt within seconds. Originally adopted by West Germany in 1979, the tank proved its worth and was subsequently exported to other nations. In fact, the Leopard 2 dominated the tank market in Europe, with only a few countries like England, Italy, and France opting for the development of their own main battle tanks. Its production began in 1979, and its initial buyer was Denmark, choosing the Leopard 2 over the American M1 Abrams due to cost considerations. Subsequently, Switzerland in 1983 followed suit, leading to other countries adopting this powerful machine. While the production of the Leopard 2 ended in 1990, this tank continues to receive various upgrades. The latest and most advanced version is the Leopard 2A7+, which many experts hail as the best main battle tank currently available. One of the most striking features of the Leopard 2A7+ is its firepower. This tank is armed with a 120mm smoothbore gun, which is a testament to its ability to engage and destroy a variety of targets, including heavily armored vehicles. The Leopard 2A7 Plus also boasts a fully automatic ammunition handling system, ensuring a rapid and continuous rate of fire. But that's not all. The tank is also designed for versatility. It can fire kinetic energy rounds, which are highly effective against heavily armored targets, as well as programmable airburst ammunition. This versatility means the Leopard 2A7 Plus can adapt to different combat scenarios, making it a formidable force on the battlefield. The protection offered by the Leopard 2A7 Plus is equally impressive. It features Chobham composite armor, known for its excellent protective properties. This tank also has additional armor modules to enhance its front protection, ensuring that it can withstand various threats. Its turret is protected by thick composite armor, providing a high level of crew safety. Mobility is another key aspect of this super tank. It's powered by a V12-cylinder 4-stroke liquid-cooled MTU 873K501 diesel engine with a power output of 1,500 horsepower. This powerful engine allows the tank to accelerate to speeds of up to 70 kilometers per hour, despite its weight of around 70 tons. It's a blend of power and agility that's essential for maneuvering on the battlefield. Additionally, the Leopard 2A7 Plus is equipped with advanced fire control systems. These systems provide the tank with excellent accuracy and targeting capabilities, allowing it to engage and eliminate threats effectively. Its laser rangefinder and thermal imager, integrated into the gunner's main sight, ensure precise target acquisition. It's an impressive fact that this tank can be configured for different roles, such as a main battle tank or an armored recovery vehicle, making it a versatile asset for any military. However, it's crucial to mention that Ukraine is expected to receive older Leopard 2A4 and possibly Leopard 2A5 tanks. These tanks boast the classic German layout with a rear-mounted engine, a self-supporting turret in the center of the hull, and control units in the front. They are equipped with Chobham combined armor and, in the case of the Leopard 2A5, additional armor modules on the frontal plate, significantly enhancing protection. The Leopard 2A4 was first introduced in the late 1980s. It is an earlier version of the Leopard 2 series and is known for its exceptional balance of speed, protection, firepower, and capacity. With a 120mm smoothbore gun, it's capable of firing a variety of rounds, making it a formidable opponent on the battlefield. The tank's armor, designed to withstand a variety of threats, provides solid protection to its crew. One unique aspect of this tank is its mobility. It's powered by a 1,500 horsepower engine, allowing it to reach speeds of up to 70 kilometers per hour. This blend of power and speed is crucial for maneuvering in combat situations. In fact, the Leopard 2A4 was often compared favorably to its contemporaries, including Soviet tanks like the T-72 and T-80. On the other hand, the Leopard 2A5 represents an evolution of the Leopard 2 series. Introduced in the early 1990s, it brought several improvements to an already impressive platform. The most noticeable upgrade is its advanced armor protection. The Leopard 2A5 features additional armor modules on the front, increasing its protective capabilities even further. This tank's gunnery systems have also been enhanced. It maintains the 120mm smoothbore gun, but with improved stabilization. Its fire control systems are top-notch, offering precise targeting capabilities. The Leopard 2A5's combat effectiveness has been taken up a notch with the addition of a thermal imager, allowing it to operate effectively day and night. Both the Leopard 2A4 and 2A5 have made their mark in history, demonstrating excellence in armored warfare. These tanks have seen action in various conflicts, proving their worth on the battlefield. They remain iconic symbols of the dedication to innovation and defense in the world of military technology. However, one of the drawbacks of the Leopard 2 series has been its relatively weak underbody protection, which ranges from 20 to 60 millimeters. In the event of a mine explosion, the driver's survival was highly uncertain. To address this, the Leopard 2A4M and Leopard 2A6M introduced a superimposed armor plate under the tank, offering greater protection. However, whether these upgraded versions will be supplied to the Ukrainian army remains unknown. The Leopard 2's turret is another area of impressive protection. It features 860 mm thick composite armor on the right side and 660 mm on the left, primarily due to the commander's EMES-15 observation unit located on the right. Additionally, the turret's side plates, angled at 30 degrees, are 310 mm thick. Unlike Soviet tanks, where all ammunition is stored under the crew compartment, the Leopard 2 wisely separates the ammunition storage from the crew. There are 27 rounds of the first-round ammunition, and an additional compartment holds 15 rounds. This design is crucial in the event of an ammunition detonation, as the blast's energy can escape through specially designed windows, increasing the crew's chances of survival. Comparing this design to Soviet tanks, where ammunition storage below the crew compartment poses significant risks in case of an explosion, underscores the Leopard 2's safety measures. The significance of Ukraine receiving Leopard 2 tanks lies not only in their exceptional technical attributes, but also in the shift from using Soviet-made tanks to NATO-standard equipment. This transition could potentially bolster Ukraine's capabilities in the ongoing conflict, as it continues to fight for its sovereignty. However, the exact impact of these NATO tanks on the course of the war remains to be seen. The Leopard 2 tank is a formidable piece of machinery, equipped with a V12-cylinder 4-stroke liquid-cooled MTU-MB 873 K501 diesel engine. It packs a punch with 1,100 kilowatts or 1,500 horsepower under the hood, enabling it to zip down the highway at speeds of up to 72 kilometers per hour. What's interesting about its drive system is that it's ingeniously designed as a one-piece engine block, allowing for a relatively swift replacement of the transmission set using a recovery vehicle, typically within a time frame of about 4 hours as stipulated by technical regulations. Now, when it comes to firepower, the Leopard 2 doesn't disappoint. Its primary armament is the fearsome 120mm smoothbore gun, the Rheinmetall version L44. This potent gun, which remained standard up to the A5 version, boasts two-plane stabilization, enabling precise targeting and the ability to fire various types of shells, including the German DM-33 Bops with tracer. This formidable shell can pierce a substantial 560 millimeters of steel armor from a distance of 2,000 meters. It's a testament to the Leopard 2's firepower. The Leopard 2 is not all about its main gun, though. It comes with secondary armaments, including 2 machine guns, one of which is coaxially mounted with the main gun, and the other serves as an anti-aircraft gun. Different variants of the Leopard 2, be it German, Danish, or Swiss models, come equipped with various machine guns like the 7.62mm MG3, the 7.62 FN MAG, or the 7.5mm MG87, depending on the nation of origin. Remarkably, the Leopard 2 stores a substantial 4,750 rounds of machine gun ammunition. In terms of targeting and precision, the Leopard 2 is equipped with a top-notch fire control system known as the MS-15, featuring independent stabilization in 2 planes. The gunner's main sight is integrated with a Zeiss laser rangefinder and thermal imager. Furthermore, the gunner enjoys an 8-fold auxiliary periscope, the Faro Z18, enhancing target visibility. Meanwhile, the commander has an independent Rheinmetall Zeiss Peri R 17A2 periscope, which provides exceptional day and night visibility of targets up to a range of 3,600 meters. The fire control system is a crucial element, providing 3 range readings to the target within 4 seconds. This data is transmitted to the fire control computer, aiding decision-making. A notable feature is that the gunner can directly see the results of these calculations in digital form. The rangefinder boasts a remarkable maximum range of 10,000 meters with an accuracy of 20 meters per 10 kilometers, which allows the Leopard 2 to effectively target and eliminate moving threats, even while traversing rough terrain. In a nutshell, the Leopard 2's technical specifications, particularly the A4 and A5 versions, are certainly on par with the most advanced Soviet T-72 and T-80 tanks. However, it's essential to mention that these NATO tanks might face stiff competition from the Russian T-90 tank, which Russia has been supplying in large numbers to conflict zones. Now, let's pivot to the heart of the matter. How could these German Leopard 2 tanks potentially influence the Ukrainian-Russian conflict? The supply of 14 tanks from Poland, though significant, might not tip the scales dramatically in a war of this magnitude. However, the implications go beyond mere numbers. For a considerable time, NATO countries were hesitant to provide tanks to Ukraine. Concerns about maintenance and repair, given that all Western equipment supplied to Ukraine is repaired in the West, have been a roadblock. Moreover, there were concerns that inexperienced Ukrainian tank crews might not fully exploit the capabilities of NATO tanks, which could potentially harm the reputation of these formidable machines. Yet, the decision to supply tanks signifies NATO's confidence in resolving these challenges and its willingness to accept potential image losses. This initial delivery of 14 tanks could potentially set a precedent for more significant support in the future. Ukraine's Minister of Foreign Affairs, Dmytro Kuleba, has stated that 5 countries are ready to transfer their Leopard 2 tanks to Ukraine. These nations include Poland, Finland, Germany, Sweden, and Spain, boasting a collective arsenal of 1,233 Leopard 2 tanks across various modifications and technical conditions. This extensive support includes 389 Leopard 2A4 versions. Furthermore, reports suggest that British Prime Minister Rishi Sunak is contemplating the delivery of a tank company of 12 Challenger 2 tanks to Ukraine. The cumulative force of these armored units represents a substantial combat capability. With such a formidable armored force at their disposal, Ukrainian troops could potentially mount a significant offensive. For instance, they might consider launching an attack on Melitopol and Berdyansk, effectively severing the Russian land corridor to Crimea. Such an offensive could be a game-changer in this ongoing conflict, inspiring Ukrainians and their Western allies and potentially leading to even more substantial arms shipments. It could set in motion a transformative and far-reaching effect. Because the Leopard 2A, 4, and A5 are just enough to help bolster Ukraine's military power, there may be no need to send the latest edition of the Leopard 2 supertank to the country. Interestingly, Germany is even working on a replacement for these impressive tanks. The Kf-51 Panther represents a quantum leap in the world of main battle tanks, or MBTs. It was created from the ground up, integrating some of the most advanced technologies available, and it sets new benchmarks across various dimensions: lethality, protection, networking, reconnaissance, and mobility. Germany will be replacing its Leopard 2S with this tank. When we talk about the Panther's lethality, we're talking about a game-changer. It's armed with the Rheinmetall Future Gun System, or FGS, coupled with optimized sensor-to-shooter links, which gives it a lethal edge. The FGS is the star of the show, featuring a 130 mm smoothbore gun and a fully automatic ammunition handling system. This combination packs a punch, offering superior firepower against all current and foreseeable mechanized targets. Notably, the autoloader can maintain a substantial 20 ready rounds, which makes the FGS more than 50% effective for engagements at much longer ranges compared to the current 120 mm systems. To add to the Panther's versatility, the FGS can fire kinetic energy rounds, programmable airburst ammunition, and the necessary practice rounds. But that's not all. The Panther also comes equipped with various armament options, ensuring it can deliver concentrated firepower for long-range strikes and against multiple targets. This arsenal includes a 12.7 mm coaxial machine gun and the Hero 120 loitering munition. The coaxial machine gun is designed to supplement the main weapon and offers a range of integration options for remotely controlled weapon stations, or RCWS. These systems enhance proximity and drone defense flexibility. Additionally, the Panther on display at Eurosatory 2022 boasts Rheinmetall's new Natter, or Adder RCWS, in a 7.62 variant. Moreover, Rheinmetall's partner, U-Vision, contributes the Hero 120 loitering munition, which can be integrated with the launcher, boosting the Panther's ability to strike targets beyond its direct line of sight. Interestingly, the KF-51 Panther is the first MBT to introduce an integrated survivability concept that's truly outstanding. This concept blends on- and off-platform sensors with active, reactive, and passive protection, not to mention a dedicated Top Attack Protection System, or TAPS. What does this mean? It means the Panther is actively shielded against a wide array of threats, particularly kinetic energy threats, all without increasing the tank's weight. TAPS works to deflect threats from above, while the rosy smoke obscurant system served to cloak the Panther from prying enemy eyes. To further enhance its survivability, the tank is equipped with a digital NATO Generic Vehicle Architecture, or NGVA, enabling it to deploy additional sensors for detecting launch signatures. This capability is complemented by the tank's ability to recognize and neutralize threats at an early stage, thanks to its pre-shot detection capability. What's more, the Panther is also cyber-hardened and designed to operate effectively in contested electromagnetic environments. When it comes to controllability and networking, the Panther offers a fresh operating concept. It's primarily designed for a three-person crew, consisting of the commander, gunner, and driver in the turret. But there's an additional operator station, which can accommodate a weapons and subsystems specialist or command personnel, such as the company commander or battalion commander. This versatility allows the Panther to adapt to a variety of operational scenarios. So, while Leopard 2 is very good and will be serving Ukraine in the war, Germany is moving on to another formidable MBT. However, in addition to the tanks to be delivered to Ukraine, Germany will also be sending the country some Marder infantry vehicles. The specific number of Marder vehicles that Germany will provide has not been officially disclosed, but German government spokesperson Steven Hebestreit indicated that approximately 40 Marders would be supplied, enough to complete a battalion. The Marder infantry fighting vehicle, a 30-ton tracked vehicle equipped with steel armor, will be another significant upgrade for the Ukrainian Army's mechanized infantry. Paired with the M2 Bradley IFVs from the United States, these vehicles offer Ukraine the mobility, protection, and firepower necessary to launch a major offensive. The origins of the Marder can be traced back to World War II, when the German army realized the importance of having infantry support to secure conquered territory. The Marder infantry fighting vehicle entered service in 1971 and has undergone continuous upgrades since. Despite its age, the Marder remains a top choice for its balance of speed, protection, firepower, and capacity. It has proved its effectiveness in various battles, including deployments in Afghanistan and the Balkans. The Marder is powered by a 600-horsepower, 6-cylinder liquid-cooled diesel engine, providing excellent mobility. Its suspension system, hydraulic shock absorbers, and advanced transmission make it a reliable and agile vehicle. It can reach a maximum road speed of 40 miles per hour, matching the speed of the German Army's Leopard tanks, and has a maximum cruising range of 310 miles. This vehicle can even navigate through deep water, fording to a depth of up to 8 feet with a kit. It can tackle steep gradients, side slopes, vertical obstacles, and trenches, making it a versatile and adaptable vehicle for various terrains. In terms of firepower, the Marder is armed with a primary 20mm Rheinmetall Mk 20H202 automatic cannon, capable of firing 1,000 rounds per minute, with a range of 2,734 yards for land targets and 1,600 yards for air targets. This cannon's accuracy and rapid fire rate make it a formidable weapon. Additionally, the Marder features a 7.62mm coaxial machine gun and 2 banks of 76mm smoke grenade dischargers. While the incoming U.S. Bradley vehicles are equipped with TOW missiles, the Marder's primary armament and secondary machine guns make it a versatile asset for both combat support and infantry transportation. Germany's decision to supply Marder infantry fighting vehicles and Leopard 2S to Ukraine, along with support from other nations, showcases the international commitment to bolstering Ukraine's defense capabilities. It's a move in the right direction. Thanks for watching. While you're still here, click on the link appearing on your screen to watch another of our interesting videos. See you there.